Hi students. Okay, so we are at chapter 9 at this point. So including this chapter, we have 4 chapters left in this course. That is Psych 218, Analysis of Behavioral Data. And this time we're going to introduce to you the t-statistic. So what this means is, last chapter we learned hypothesis testing, or the introduction to it, using z-scores and z-distributions as our null distribution. So here, we're going to use the t-statistic for situations, and this is a lot more common, where we don't know what the population standard deviation or even what this population mean is. So t-statistics are its own set of distributions with its own scores. They are still location scores, but there is one big factor for t-statistics, and that is, well, instead of working with population standard deviation, we're going to use sample standard deviation. And so we're going to keep two things in mind. One, the t-statistics are going to be based more on sample distributions, although the t-distribution itself is still a sampling distribution. So we're going to need a sample standard deviation for our standard error. And we also need to account for sample error. That is sampling bias. That is, well, we're collecting data from the sample and we have no parameters to work with, and we're estimating the population, making a sampling distribution entirely on sample data. And so we need to account for something called degrees of freedom. So if you remember, when we do variance and standard deviation with sample data instead of population data, we use n minus 1. So when we look at sample standard deviation and use that as an estimate of standard error for the t-distribution, we need degrees of freedom. So two things to keep in mind right now. It will become more clear as we look at those t-distributions. So there are 5 learning outcomes for this chapter, and they are: 1. We want to describe, or be able to describe, how to use and when to use the t-statistic instead of z-scores when we do hypothesis testing. Again, the base assumption is, well, we don't have the population standard deviation or even the population mean to work with. We're working entirely with sample data. 2, we want to be able to perform hypothesis testing using the t-tests. That includes using t-scores and from t-distributions instead of z-scores from z-distributions. Next, for tests where we have decided based on statistical evidence that we decide to reject the null, we would also want to evaluate effect size using Cohen's d. We also want to find other ways of measuring effect size for this chapter, and one of these would involve the percentage of variance accounted for or explained. And that is noted as R, with the notation of R squared. And finally, we want to begin learning how to compute a confidence interval. We'll go into what that means as well. So the math tools we're going to need for this chapter, well, some of these might be familiar to you already, or at least when you see them, it'll make sense. So for example, because we're working with sample data and statistics, that is sample statistics like sample mean and sample standard deviation, we're going to need to make sure we know how to calculate sample standard deviation and why we calculate it in a specific way using degrees of freedom. That's going to be important to us. Next, we also want to see how standard error is different in t-distribution or t-tests. And so a sound knowledge of things we learned before from chapter 7, like the sampling distribution, sampling statistics, and the theorem that helps us do it, that explains how we can do it, the central limit theorem, would be useful as well, and how sampling distributions work. And finally, because we're doing hypothesis testing, we want to make sure we know the logic, the steps, the direction, the critical regions, the test statistic, the decision, and the types of errors we can make in hypothesis testing as well. Again, as you can see, in this class, the skills and concepts are cumulative, so make sure you are fully aware of what's needed, and you're fully prepared for this chapter as well, with chapters 4, 7, and 8 for sure. So, to review, when we do hypothesis testing with Z, it is in some ways, as you will see, easier than t-test because we are given some parameters that will help us estimate the population, and that is estimating the standard error. So here you see the standard error that approximates, what's the expected difference between the sample mean and the population mean. We are given the population standard deviation, which is great for this. And so now we estimate it by dividing the standard deviation of the population by root n, or dividing the variance of the standard deviation by n and then square rooting everything. So that's again a review of the standard error for Z or Z tests. When we work with Z tests, again, we're using Z scores or Z scores. So for hypothesis testing, notice the changes here. We're doing M instead of X and sigma M standard error instead of population standard deviation. So this is what this says. The Z-score is the obtained difference between the data and the hypothesis, that is the sample data, sample mean, and the null hypothesis, divided by the standard difference, standard deviation between sample mean and population. Again, the assumption for these distributions to work is that we're working with a sample size that is 30 and larger, and the population distribution is normally distributed, at least approximately. Again, if these things seem totally new to you, or they seem a little confusing, more details, you can review these in chapters 7 and 8, where we talk about sampling distributions and hypothesis testing, the introduction. So a word of caution then, we can't use Z-scores for everything. And there are two reasons for this. One, we often don't know what the population standard deviation is, or is this not given to us. Again, remember how large populations are, at least the ones we're interested in. Think of recent cases like COVID-19, trying to measure entire nations or even the world. Trying to collect data from everybody, it's going to be impossible. So since we don't have everyone's data, we wouldn't know what the population standard deviation is. We can only estimate it. Also, when we work with samples, well, we would only have sample data. In recent events, well, certain countries, including Canada, is trying to figure out, test a vaccine for COVID-19. At the time of recording, this is what's happening. And so they had phases, and the first phase, they can only measure 100 people. And so, again, instead of population of Canada, which is in the millions, well, the sample here is only 100. And so what we would have then for something like this, whatever sample you have, and even in your surveys and your projects in your research methods class like Psych 217, your sample size and sample scores is really what you have. And that's kind of it. So the data you can get then from that stuff is your sample mean and your sample standard deviation. Something to note though is that although we won't have population standard deviation or even population mean, we will always have, if we're doing our research using random sampling and collecting data, and as long as we have enough data, then we can always calculate the sample mean and the sample standard deviation. And in this course, when you do hypothesis testing, you're always going to have at least the sample mean and the sample standard deviation. If you know you're going to have the population standard deviation, then you can use a Z test. But if you don't, then this is what we're going to do now, a t-test. So this is our solution in this course. So when we don't know parameters like population standard deviation or even population mean, we're going to need another distribution to work with, or actually another set of distributions. And you'll see why I'm using this type of language in a minute. So we're using the t-statistic that involves t distributions. So t here would be considered an approximate z, and it will be approximate depending on what your sample size is, and that would directly affect what the degrees of freedom is. And remember, degrees of freedom is, right now, I'm just going to tell you this, and it will come back to you, n minus 1. Again, we're trying to account for sample bias. So the estimated standard error using the degrees of freedom would be used instead of the real standard error, that is the population standard deviation divided by root n. We don't know this, so we need to use an estimate standard error, which is s with the subscript n. So here it is, the next slide. This is our estimated standard error. Again, the concept is the same, except we plug in different values. This time, instead of using population values like sigma squared, we use s squared. Again, this is because we're using sample data. So the estimated standard error is, well, we have the population, well, we have not the population standard deviation, the sample standard deviation, which you'll need to calculate, by the way, using degrees of freedom. So remember, this would be n minus 1. Now, to estimate standard error, we note the sample size, just like we do with our population standard error, the real standard error. And the estimated standard error would be, well, s for sample standard deviation over square root of n. Or we can also use population sample variance. You can see even I get confused as I say it. So make sure you know when you're using estimated standard error, you use sample variance or sample standard deviation. So s squared here is sample variance. I'm just going to write VAR shorthand for now, and then over sample size, and then you square root of that. Again, so we're clear, it is an estimated standard error. And we estimate the real standard error with the estimated standard error where we don't know the population standard deviation, and therefore we don't know what the real standard deviation is, or the real standard error either. So the t-statistic works just like the z-statistic, except for what standard error we use. So to compare then, I'm just going to draw a big line right here. Your z-statistic, I'm just going to put observed here because that's what we're using. We're using an observed value. That is the sample mean. So both cases we have the difference between the sample mean and the population mean. In your z-statistic, we use standard error, that is the real standard error, when we happen to know the population standard deviation. Here, we use the estimated standard error. So that's what this is right here. And so instead of using your z-statistic, we're going to use the t-statistic to test our hypotheses. And usually that is going to compare the sample with the population when we don't know what the population standard deviation is, or when we compare one sample to another. So the first thing we said, sample to population when we don't know the population standard deviation, that's chapter 9. That's this chapter. When we compare two samples, that's next chapter, independent samples t-test. Well, that's one type of comparison between sample to sample. So a major factor in our t-test is that we must account for sample bias. That is degrees of freedom. Now this whole process starts because we are calculating sample variance and therefore sample standard deviation. I'm just going to write SD for shorthand. So a lot of things we are using is from the sample. Sample mean is from the sample. So because we calculated the sample mean first, that means only n minus 1. If sample size was 20, then only 19 scores from the sample are now independent. And we talked about this last time in terms of degrees of freedom, so then you can review that in the measures of variability chapter 4, where we talk about degrees of freedom. But quickly to review, it's like this. If you have 3 values, and I divide this by the number of values there are, and this is, I get the mean here, 6 divided by 3, that's 2. I'm trying to get the mean here, assuming this is the sample. Then, if I happen to know the mean and what is used to calculate the sample mean, that is how to calculate the sample mean, the formula, then if I only erase one value, you can figure out what that value, missing value, definitely is. So that value can never be anything else, so it's not independent. It depends on everything else. However, if you start missing other values, let's do the opposite here. I'm missing 2 values and I know one of them. Then the missing block A and the missing block B could be anything. It doesn't have to be just 2 and 3. It could be 1.5 and 3.5. It could be 0 and 4. It could be a whole bunch of things. As long as the mean remains 2. So the possibilities is potentially infinite. Whereas if you're only missing one value, and that is your degrees of freedom, then you're only left with one possibility. Therefore, it's no longer independent. And so this is factored in to account for sample bias, and we also need to factor this in when we do our t-test. And therefore, what we're going to need to look at our t-distributions, and I'm going to show you this in our t-tables, is the degrees of freedom. That is n minus 1 right here. So I'll write it big here. To review, you need to know that degrees of freedom, we use it to calculate sample variance, and we're also going to need it to use for t-statistics and t-scores. That is to determine what our t-distribution is along with its critical values. And this slide shows what that means. So we'll show this distribution in the slide first. Notice that as sample variance increases, your degrees of freedom also actually decreases. Well, because you're dividing it by a smaller number. So just to review, right? If you got your sample standard deviation, okay, so that sum of squares divided by n minus 1. Right? N minus 1, as you remember, is degrees of freedom. So one thing to note here, when you look at degrees of freedom, you can also tell what sample size is. Well, in this case, if the degrees of freedom is 20, well, the sample size is 21. N here is going to be 21. If degrees of freedom was 5, well, the sample size was 6. So remember, when you determine degrees of freedom, you need to know what n is first. And then, to get degrees of freedom, you subtract n from 1. For these distributions, where it has the mean of 0, because these are still standard normal distributions, where t-scores are still location scores, the shape of the distribution changes when degrees of freedom changes, because we talked about last time, sample size has a direct effect on standard error. And so for each different sample size, you're going to work with a different t-distribution. And in general, the shape goes like this. In a normal distribution, that is a Z distribution, where degrees of freedom is now infinite, because we happen to know the population standard deviation. That means we've basically done everybody. Then it would have the same shape as a Z distribution. But as we go with smaller samples, the distribution of the t with lower degrees of freedom is going to get shorter and shorter and shorter. So if there was a degrees of freedom 1 where you only collect a sample of 2, it would probably end up being down here, like really flat. Like this. So this would be the, like, probably really the lowest you can get for now. I'm just going to use the degrees of freedom of 1 here. That's kind of it. And the sample size for degrees of freedom of 1, well, it's going to be 2 minus 1. Well, the sample size is going to be 2. So again, the higher the degrees of freedom, the closer it would be to the normal distribution, that is your Z distribution. And I'm going to show you that right now. So remember, we've been working with the unit normal table before that uses Z-scores and uses Z distributions. In your modules, you can go to your course materials and your statistic resources, and you find the t-table. So in this one, if you're taking this class at Alexander College, you go t-table for hypothesis testing, and you'd find this table right here. Now I just made this larger, made it as large as I can here on the screen, and you can see several things. This table reads a little bit differently from your unit normal table. In fact, this table makes some assumptions. One, it assumes you know how to read a table like this. That is, you know how to read a unit normal table. Two, it doesn't have all the t-scores anymore. It only has specific ones. That is the ones we use specifically for hypothesis testing. So these are the proportions that you're going to get, and that's it. So these are all basically alphas. And the two-tail, these are going to be, for a two-tail test, you would look here. And notice the proportion of the two-tail test row. For example, here for an alpha of 0.05, the one tail here is going to be split to 0.025, whereas a one-tail test with an alpha of 0.05 would have a two-tail test of 0.110, because 0.1 is going to be double of the 0.05. And that's all you get. So mainly for our course, we would focus on the following. If you got a one-tailed test and you set alpha at 0.05, you would look at this column right here. So you count 1, 2, 3, 4, 5, 6. And this is kind of like the basic way of doing it, or I'm just giving you like the hand you down, here, give me answer. But again, if you know how to read, oh, okay, these are cumulative probability values, like your alphas, and you know, oh, the first row is one tail, like the whole tail, like this. Again, it could be positive or negative. I'm just going to use the right tail for now. And then two tails is where the alpha is split into two tails. In the next column, you see, okay, well, for two-tailed test of alpha 5% or 0.05, well, each tail is 0.025. So you read the values, the critical t values from the 1, 2, 3, 4, 5, 6, the 7th column here. Again, if your course or your research makes you do a more stringent or stricter test where you use an even smaller alpha, well, you could have a two-tailed test of 1% for alpha, or one-tailed test with an alpha of 1%. You would use the appropriate column. The other columns we don't really use, but it's meant for it's there to help you understand several things. One, here the first column, well, if you set alpha at 100%, well, you don't need a critical value. It's just, well, it won't exist. You'll be rejecting null every time. But as you increase alpha, you're going to be less likely to reject the null. So, to summarize, when you use the t-table, you need to factor in some things. One, we are only working with critical values. That is our critical regions, either alpha at 5%, one tail or two tailed, or it could be alpha at 1%, one tail or two tailed. So we will look at the specific columns for these. Next, in the rows that are below these critical regions, we have degrees of freedom. As you notice, as degrees of freedom increase, the critical values decrease. So if you have a sample size of 2, and the degrees of freedom that is 1, 2 minus 1, then the critical value for a two-tailed test at alpha equals 5%, the critical t-value is going to be 12.71 standard deviations away, or standard errors away from the population mean. As you increase in sample size, you'll notice in the same column that the standard error decreases, and therefore the critical value also decreases. So as you approach infinite degrees of freedom, so again, for example, if you have sample size of 10, you'd look at degrees of freedom 9, not 11, and then you'll see the critical value here is 2.262 for a two-tailed test where alpha is at 5%. So I'm going to scroll down now. So as you can see, as sample size increases, you're going to get a slower critical value. And as you can see here, remember, this is the column where you have a two-tailed test where alpha is at 5% for all of alpha. So each tail would have 2.5%. Here we will explore that confidence interval as well, and it corresponds to 1 minus alpha, which is 95%. The z-score, then, where the degrees of freedom is infinite, is the same critical value as in the one for the z distribution, 1.96. The next one up would be a degrees of freedom of 1,000. Let's say if the sample size was 1,001, then you would have something very close like 1.962. More realistically for us, where we have samples of maybe 20 or 30, so then the degrees of freedom for a sample size of 20 would be 19, and the critical t-value for that same test would be 2.093, which is still larger than 1.96. And if you had a sample size of 30, then our degrees of freedom would be 29. Just writing the sample sizes here. And then the critical value then for a sample size of 30, where degrees of freedom is 29, is 2.4045 in a two-tailed test for alpha at 5%. So that's how you would look for critical values, and this is your step 2, and set critical regions using the t-distribution. And this is very important. Remember, you're reading this particular table for the right critical regions, one tail or two tail at alpha at a certain percentage, and then you got to find the corresponding degrees of freedom depending on your sample size. And degrees of freedom is n minus 1. N minus 1. Okay. All right. So having looked at the t-distribution or t-distributions to figure out where to set our critical regions and find our critical values, these are the points that were mentioned. First, your t-distribution, as you've seen in the table, is actually a family of distributions where instead of working with one normal distribution that is standard normal distribution with z-scores, now you're working with a whole family of t-distributions dependent on the degrees of freedom, that is sample size. So there's one t-distribution for each value of the degrees of freedom that is on the table. And again, even the table doesn't show every degrees of freedom either. It just, after 100 or after 40 or so, it jumps by 10 degrees of freedom, and then eventually 100 and then 1000. But because we usually use sample size much smaller than that, so we have like 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, all the way up to 30 at least. So then we have individual degrees of freedom there. Again, these family of distributions approximate the shape of the normal distribution. So unless it's the normal distribution where the degrees of freedom would be considered infinite, they are going to be flatter than the normal distribution, as you can see from slide 11, the previous slide. They are also wider, that is more spread out than the normal distribution. And so in that sense, they have greater variability and their tails are quote-unquote fatter. Therefore, in hypothesis testing, we need to make sure we're using the right values for t in the right t distribution depending on your degrees of freedom. And you determine that by your sample size minus 1 instead of using the unit normal table. So here's an example. What we're going to do is look at this example and use the t-distribution table to see for ourselves if these values are accurate. So we have a degrees of freedom that is free. Take a moment and see what the sample size is for this particular t-distribution. If you answered 4, then you're right. And again, this would be a null distribution for now if we're doing a hypothesis testing, but we don't have to write that yet because we're not testing a hypothesis. We're only looking at the t-distribution. Again, the t-distribution is still a normal distribution in the sense that it is normally distributed, but it is not the unit normal table. So it has a mean of 0, and these are t-scores in here. And its shape is determined by the degrees of freedom. And let's say we want to set alpha at 5%, but here it's 5% each. So alpha really is 10%, or 0.10. And these here are alpha divided by 2. So each one of these tails is 5%. So the value we're looking for in the t table for degrees of freedom that is free, well, we'll have to see if this matches. A degrees of freedom that is free in a two-tailed test where each tail has 5%, we're going to see if the critical value is indeed 2.353. So we go back to our t-table, go to the right column first. Oh, okay, it's a two-tailed test, and the two-tailed test here is 10%. And so you can see here, double check that, oh yeah, for a two-tailed test where alpha is at 10%, these are, remember, alphas by the way, the top row is one tail, so it's alpha divided by 2. Then this, right, yeah, each tail here would have 5%. So we're looking at this column. So we count, just in case we need to scroll down. 1, 2, 3, 4, 5, 6, the sixth column. Well, because degrees of freedom that is free, we don't really need to. Then we find the right row, that is here, oh, free. And we locate the value in the matching column. So third row down, sixth column to the right. And so the value here is indeed 2.353. And so this result then would give us a few things. One, we have found the degrees of freedom that we need. And we have used that in conjunction or with the alpha that we've set, as well as whether it's a one-tail or two-tail test. Usually it will be a two-tail test. And then finding the right critical value in the t-table, where we match degrees of freedom with the appropriate critical region, one-tail or two-tailed. So yeah, so far so good. So in terms of getting the observed statistic then, it's still the same. For now, we're working with one sample, and we compare that from the population. But we don't know what the population standard deviation is. So we estimate standard error. And so the t-observed statistic is going to be the difference between the sample mean and the population mean. And by sample mean here, we're talking about the treated sample. And well, at least when we do when we test for treatment effect. And so instead of using sigma m, that is the real standard error, we use the estimated standard error, lowercase s with a subscript m. Again, if the population mean is exactly the same, or as the population mean, it's the sample mean. If those two means are the same, then the t-score would be 0, and you wouldn't make a decision to reject at that point. But we're looking for something that's probably greater than 0. And we'll be comparing that with the critical value that we found, just like what we did here in slide 13, with the example with this particular t-distribution right here. So here's what the comparison would look like. So here we have a known population before the treatment. So that's basically, everybody that's before the testing was done, before we do the hypothesis testing, before we do any research. So let's say we're working with a distribution where we happen to know the population mean, but we don't know what the population standard deviation is. We somehow don't know. And often we don't. So we administer treatment, grab a sample using random sampling, and we randomly assign them. So this particular sample has been treated. And so we're trying to determine whether that treatment has any effect. And we're trying to figure out what this expected effect is. Again, we're trying to see if there is a quote-unquote statistical significance, or whether the evidence supports our decision to reject the null. And we'll be using the t-statistic to do this. And to do that, well, we'll do hypothesis testing, and the 4 steps are the same. So again, last chapter, Introduction to Hypothesis Testing, provides a foundation for us to do basically everything else in this course. All the other chapters would involve some kind of hypothesis testing. So this time we're doing hypothesis testing with t-scores and t-statistics in t-distributions, but the steps are the same. So again, here to review, step 1, state your hypotheses. That is your null and your alternative. Again, depending on what you're trying to research, the alternative hypothesis would either be looking for a difference or looking for an increase or decrease, and the null is looking for no difference. You also select an alpha level as well in this course, because we're not actually doing any particular research per se, but we're using research data. Then the alpha level would usually be given to you. In more advanced courses, you will be asked to set an alpha and explain why you set it as either 5%, 1%, one tail, two tail, and so on, depending on what the situation is and what the stakes are. So for example, if it was a medical test, like a clinical trial for the COVID-19 vaccine, you probably want to raise the stakes a little higher than, let's say, if it was a tutoring company that you want to see if the tutoring works. Next, you want to set a critical region, locate that, and find the critical values using the t-distribution table and the degrees of freedom determined by your sample size. Remember, degrees of freedom is n-1. Then you calculate your test statistic, which first you need to get the standard error, and then once you figure that out, you can calculate your test statistic. And then finally, you make a decision regarding the null hypothesis, whether to reject or fail to reject, depending on how your test statistic compares to your critical value. So, in terms of practice questions for these steps, we have a Chapter 9 worksheet, just like we had a Chapter 8 worksheet, and you can find these in your discussion topics right here if you're taking this course at Alexander College. And so, let's quickly here, you can see in the discussion board, you got chapters 8 and 9. So if you go to 9, you can go down to the link and click this. It should open up the same thing that I just showed you, just smaller. I zoomed in here. So then there's a few questions. There are a few questions here that you can use to practice your hypothesis testing. And it actually makes you do some calculations first. So you just get your sample scores. This is more similar to what your research would be doing. And you would calculate your deviation score, your sum of squares, and then you get your sample variance and sample standard deviation. Remember to use n-1 here. And then for each of the scenarios, you'll do your steps, figure out effect size and so on. So up until this point, you'll be able to go up to steps 1 to 4 and even 5 maybe, based on everything that's done so far. And if you have read ahead and figured out how to do Cohen's d and r squared and confidence interval, you can try those too. So again, there's 1, 2, 3 questions. Let me double check here. 3 questions that you can practice. Each one of these questions would ask about a particular sample in a particular situation with a particular alpha level that you would use. So again, the sample sizes are going to be different. The alpha is going to be different. And if you don't see one, use 5%. But you can figure out whether it is 1 tail or 2 tail depending on the research question. So that's that. So again, if you don't see a particular alpha level that you should set, use 5%. And then you need to determine by reading the question whether it's 1 tail or 2 tail. In certain questions where you are asked to use a specific alpha level, use that. Here in this case is 1%. Again, you need to determine if it's 1 tail or 2 tail. So in this question, for example, it says different. Now asking for an increase or decrease, that's going to be a 2 tail test. Something to keep in mind. So here's another example then with a larger sample size. Again, let's use this one as another example to see if we're doing things correctly. So this would be step 2 here. We have set our alpha. And again, we're using 2 tail tests. So each of these is going to be split in half. No, not 0.05, but 0.025. So that's that. Okay, degrees of freedom is 8, so sample size is 9. Here it is, a null distribution. We're doing hypothesis testing with this. And that would be 0 here. And again, these would be t-scores. These would technically be sample means, by the way. Transformed into t-scores, etc., etc. Okay. So let's take a look. Okay, we have our degrees of freedom is 8. We set our alpha at 5%. It's a 2 tail test, so we split the alpha in half. And so in the table here, so it's a 2 tail test where alpha is at 5%. So we're looking at 1, 2, 3, 4, 5, 6, the 7th column. Okay. Again, each tail would have 2.5%, so it checks out. Next, we need to figure out what degrees of freedom we're looking for. 8. So we find the corresponding row and match the column. So this should say 2.306. 2.306. So let's double check here, see if this is right. Yes, 2.306. So again, anything that is more extreme, we reject the null, and anything that is less extreme, we fail to reject the null. So next then, let me just close everything first. Okay. Again, we got to make sure our assumptions for the t-test is covered as well. So first, we want to check our assumption that the values in the sample are independent observations. And those are usually done through random sampling. Every participant has an was from the population that had an equal chance of being selected and assigned, and that these participants, as they do or as they're part of the research, they're not influencing one another. Also, we want to check our assumption whether the population that is being sampled is a normal distribution. That is, the population is normally distributed. Something for note here in advanced courses. For now, we assume, the questions assume or make these assumptions. In advanced courses, you'll be asked to test those assumptions. And if the assumptions don't work out, you might not even have to do the test. So in large samples, again, this would be for more advanced courses, this assumption, that is, the population is normally distributed if the sample is large enough. So again, if it's going to be 30 or more or even larger, then yeah, the population might not be normally distributed where the sample came from, but the hypothesis test then could still be valid. So, having covered the steps and having covered t-distributions and when are we supposed to use t-tests and what the conditions are, let's do some learning checks before we end part 1. So question 1. When the sample size is small, less than 30, the t-distribution is... You have 4 choices here. So A is almost identical in shape to the normal Z distribution. B is flatter or more spread out than the normal Z distribution. C is taller and narrower than the normal Z distribution. Or D, well, can't really say. Therefore, hypothesis test would be impossible. Take a moment and think about what the sample size influences in terms of degrees of freedom and standard error. And think about how that would change the shape of the t-distribution. So if you said flatter and more spread out than the normal Z distribution, where the degrees of freedom for that one would be considered infinite, then you're right. So to review here, you can see slide 11. As you can see, as the distribution has small degrees of freedom, well, it gets shorter and wider. Flatter and fatter, so to speak, quote unquote. Again, the tallest and narrowest distribution would be the Z distribution, so there's no way that a T distribution would be any taller and narrower. And so the correct answer here is B. Okay, 2 true-false questions. A, by chance, 2 samples were selected from the same population, they have the same size and the same mean. That means they'll also have the same t-statistic. True or false? And B, compared to the Z-score, a hypothesis test of a t-statistic requires less population about the population. Again, think about these statements in terms of sample size and sample mean. What happens when you get 2 samples from the same population with the same size and the same sample mean. And then for Z-score, in comparison to a t-statistic, think about what information is required for a t-statistic. So for the first statement, it is still false because the t-values would still be unlikely the same because the standard deviation or the variance estimates would still be different. Remember, we've only described sample size and sample mean. We have not talked about the sample variability. So again, they could have the same mean, but one sample could have a low variability where the distribution is a lot taller and narrower, and the other distribution could be much shorter and wider with a larger variability. But they could still have the same mean. So, you can still have 83, and you could still have 83 for both of these distributions, and n could still be 36. So because we haven't, and the statement doesn't say anything about these distributions having the same variance, then there's no way for us to say they're going to have the same statistic. T-statistic is actually going to be different because the variance is going to be different. And in statement B, compared to a z-score, yeah, your t-statistic does not require the population standard deviation, but your z-test does. So that's it then. Before we go into effect size, make sure you review your 4 steps in hypothesis testing, as well as making sure you can describe and apply the differences between a z-score and a t-score, a z-distribution and the family of t-distributions, as well as how samples work, like the size, the sample mean, and the sample standard deviation, and how that directly influences not only the estimated standard error, but what t-distribution we're using, because we're using different degrees of freedom for each different sample size. So again, you can use your resources. You can use your practice questions in the Chapter 9 worksheet if you're taking this course at Alexander College. Or you can use our web resources, including our web tutorials. Make sure you use Microsoft Edge or Apple Safari for it and enable Flash. And you can use your textbook as well, which is plenty of questions for you can practice step by step. And if you still have problems with these, you can contact me at my college email address. If you're taking this at Alexander College, you can contact me by the Alexander College email address. So until then, make sure you practice these steps with now t-scores and t-statistics and t-distributions. Again, we do these when we don't know what the population standard deviation is, or sometimes we don't even know what the population mean is. But for Chapter 9 for now, we know at least the population mean, but we don't know the population standard deviation, so we need to use the t-statistic, along with all the steps that are involved there. So until then, we'll see you in the next one.